This is Pat Spoden with the National Weather Service in Paducah. Today we're going to talk a little bit about responsible forecasts and how things have changed with the internet and social media. Now this presentation is intended for emergency managers and the media. And we all know there's a lot of good information on the web, a lot of great weather information. However, there's times where we need your help. Anyone can be a weather forecaster with the aid of the internet and social media. And sometimes it's great help and other times not so much. The more time that we have to spend squashing rumors, the less time we have to focus on your forecast. So we're asking you to help us stop some of the rumors that go on at times. I think the most important thing is to not get sucked into the hype. Just beware of any rumors that you see on social media or on the internet that are talking about, just amazing snowfall forecasts, super high amounts, 30, 40 inches, or that every time there's a chance for a tornado, the tornado outbreak of the century is coming. You'll notice that sometimes these people who do this, they focus on this and they forecast it on a regular basis. The main thing is relax and check our website for information. Everyone wants to be able to say that they were the first one to get you the information, that they all want to be believed. And sometimes this leads to jumping to conclusions and finding the most disastrous possible outcome in order to get everyday people hyped up about every storm that comes through. As I've already mentioned, some of the internet wannabes look for the worst possible outcomes. Sometimes they may work to even discount what we're doing. They often prey on people's fears. They want to see people jump. Usually what happens is look at one long-range model and say, this is what is going to or even could happen. For instance, looking at the GFS out at 360 hours, which is 9 or 10 days away, and saying, look what's going to happen. And it just tends to get people all riled up. So as this picture puts it so well, the idea is to be responsible about what is posted out on the internet. So what does it mean to be responsible when it comes to forecasting? Well, responsible forecasters will wait until the confidence is moderate to high before bringing the information out, as things change dramatically when you're looking out 5, 6, 7, 10 days out. And there is a clear difference between getting information out early and getting realistic information out early. If there's a major storm headed our way, we're going to be able to let you know several days beforehand in most cases. And we will not sensationalize a particular storm unless it is absolutely necessary. So what does this graph mean? Well, basically it's saying when we're trying to forecast out to years, seasons, months, even sometimes 8 to 14 days, our forecast confidence is generally pretty low. However, as we get closer, our confidence level becomes higher and higher that something is going to happen, or at least the potential is there. So why is there uncertainty with the forecast? Well, this graph kind of explains it some ways. We have limitations with the observations that we actually get. There's sometimes errors with the data. There's a lack of data at times and locations where it's needed, especially like over the oceans. There's just not a whole lot of data there. But even locally, sometimes there's areas where there's just not a whole lot of observations. Sometimes even the data conflicts itself. There's also scientific limitations. We just don't truly understand how the atmosphere works. So we write these programs, these numerical models, that using equations to try to represent a very complex process. And sometimes there's even limitations in computer processing time, which can add to some of our uncertainty. So let's talk a little bit more about forecasting. Now, uncertainties in the forecast are due to the complex nature of our atmosphere. The numerical models, which you hear people talk about, attempt to determine how the atmosphere is going to evolve over time. So you've heard the term numerical models. Well, what do? Well, they attempt to simulate the atmosphere. The accuracy is limited by how precisely they can represent a very complex process. And added to the problem is how the atmosphere works exactly is really unknown. So there's a lot of guesses going on. Now, we've made a lot of strides, especially over the past 50 years, that have really improved our knowledge. And each model type has different physics. In other words, how that model thinks the atmosphere actually works, and thus will likely produce slightly different outcomes from each other. Now, here's just a sampling of some of the numerical models that are out there. GFS, the Canadian, ECMWF, which is the European, the HER model, Ensembles, UK. There's literally dozens, if not hundreds out there if you include all the local models that are being run at some offices. Each model has its own physics or interpretation of how the atmosphere works. Now, this process can become more complex and more wide-ranging than just the actual models themselves, as we can take different pieces of the models and put them together or separate them out and come up with lots of different local guidance. That some offices have this, where you're creating different temperatures, dew points, winds, and wind gusts from all different types of guidance that's out there. It's interesting that over the past, I've seen some remarks on social media about, well, how come the forecast changes? I thought this is what's going to happen. Well, we run these models several times a day, some of them hourly. The newer runs obviously have fresher observations, more recent observations. And we use this information to continually revise the forecast, and that's why they change often. We always work to adjust the forecast to the most likely outcome. So why aren't the forecasts accurate? Well, there's many reasons. Some of them we already talked about. Limitations of observations. Not enough when we need them, especially over the oceans. Errors in the observations, inconsistencies with the observations. And again, probably the most important thing, an incomplete understanding of the complexities of the atmosphere. Okay, we've talked about forecast models, but how do forecasters use this information? Well, we evaluate the model output. We incorporating knowledge that we have of model strength and weaknesses. So one model tends to do better in this type of pattern, another one tends to do better in that type of pattern. Other things we look for are consistency from run to run. If the model produced a storm, for example, next Friday, and the next run also has it on Friday, well, that helps in the consistency. We also look at how the model compared to the real world when it started. So when we started the run, say we ran it at 6 o'clock last night, how did it look right then compared to the real world? We also compare to other models, like how the GFS and the European may agree or disagree on a system. So how does a typical forecast occur? And a lot of this has to do with the uncertainties that are involved in our science. So say we're looking at a chance of a storm moving into the area. At 5 to 7 days out, we're generally looking at chance levels, like a 30 or 40% chance that snow or rain or sleet or something's going to happen. If we move into areas where we're above 50%, say if we're looking at 60%, we're feeling pretty confident that something's going to happen. But knowing that models are changing often. Remember, we run them several times a day. Now, as we get closer to the event, that initial chance precipitation can evolve in different ways. One, the chances increase. That means we have increased confidence that something will happen, or the fact that it may cover a larger area. If the chances remain the same, a couple different things are possible. We're not very confident the event will happen, or if it does happen, only part of the area is actually going to feel it. Or the chances can go down, which means the chances of the event even occurring are decreasing, or the expected coverage were probably lower than previously thought. So what does it mean when you say, oh, there's a 100% chance of rain tonight? Actually, what it means is that during that time period, there'll be at least 1/100th inch of liquid or liquid equivalent fall into a rain bucket that night. It does not mean that it's going to rain all day or all night, just that it will rain. Okay, now we're going to add a few more layers of complexity on top of it. there's a thing called Ensemble Forecasting. And this has been developed over the past several years and has really become a big improvement to our forecast alone. And what we can do is we can take a certain model, actually any model, and run it several times. We have slightly different initial conditions, and we see if they can agree on the location and timing of a particular storm. Now, if different runs, which we call ensemble members, do not agree on the timing or location of a particular storm, then our confidence in our forecast for that storm system will be lower. However, if they agree well, then the meteorologist can be more confident in their forecast. You look for higher precipitation chances. And we can also look at ensemble of various model types, which means ones that have different physics. And again, the more they agree on a particular storm system, then the higher our confidence will be that that storm system is actually going to occur in that time. Okay, here's an example of some of the output we get from these ensemble models. Here we're looking at 850 temperatures and 850 hectopascals or 850 millibars, about 3,000 to 5,000 feet up off the ground. And if you look at this, note the different locations of the 0 degree line. One model has it up through central Illinois, another one's down in the Ohio Valley. Next one's down in Tennessee, northern Alabama, maybe even down to Savannah, Georgia. So all these different models putting together, they really can't basically agree. So one of the ways to clear that up is to just, what's the average or what's the mean of where the 0 lines are if you take all those together. So let's take that same process and put it over the Northern Hemisphere. This is looking at ensemble mean forecast for 500 millibar heights. So it's about 18,000 feet up. And you can see different waves in the pattern here. And it all looks really nice and smooth, and the colors look great. So you're thinking, wow, that looks pretty good. But when you get down and you look at the individual runs, you get this. This is what we call a spaghetti plot for good reason. Now, who's to say that one of these lines, which represents one model run, is better than another one? So you can see where the models somewhat agree, and you can see where there's lots of discrepancy between the models. And so we try to look at a spread. How far apart? Where are they most likely to agree? Where are they not agreeing? So that's just some of the complexities of looking at ensembles. Okay, so we talked quite a bit about numerical models and how forecasters put things together and the responsibility factor involved in all that. Well, it also depends a little bit on where you get your information and why is it that you can listen to one radio station, you get a forecast, then a different radio station, or the same thing with television stations. The National Weather Service gives out all of our forecasts, and along with model data, radar data, satellite, it goes out for free. Now, individuals and private companies can take this information, repackage it, and or modify it to create their own forecast, and that's fine. Now, many radio stations employ private meteorologists or companies to provide you with weather forecasts. They may or may not agree with the National Weather Service, and that's okay. TV stations employ meteorologists to provide you with weather forecasts. Again, they may or may not agree with the National Weather Service. Then there's larger stations or larger companies such as the Weather Channel. They are a private company and they employ meteorologists to create their forecasts. Once again, they may or may not agree with the National Weather Service, and that's just fine. That's how the weather enterprise works in the United States. Now we realize that this occurs, and we also realize that most people get their information from the media. But the National Weather Service works closely with these partners to ensure that watches and warnings are available to you. Thank you for listening.